talk about creating and managing virtual hard disks, virtual machines, and checkpoints. So a lot of this is very easy knowledge because we have some background in virtualization, VMware Workstation, and also in the vSphere now. So you'll see that a lot of them are equivalent. They might be called something different, but basically they're equivalent. The idea, the theory, the understanding is equivalent. So today we're going to look at the virtual hard disks. Let's start with that. So yeah, so that's basically just an overview of what we're going to talk about here. So what are the storage options for your virtual machines? So virtual hard disks are directly attached disks. So basically, what does that mean? They're basically equivalent to your hard drive that you have inside your computer, but on virtual machine. Supports two types. We've got the IDE, which is, that's a bit old, isn't it? That's old physical type. If you remember the ribbon cable, the wired ribbon cables you used to plug into the hard drives. Sorry, Master today. That's right. That's what the IDE is all about. And as you can see, this is only for generation 1 virtual machine. So very basic old generation of virtual machines. You have two IDE controllers, just like in a real machine. And you can boot from an IDE, but you cannot modify the devices while the virtual machine is running, which makes sense. Okay? If you think about a virtual machine like a real machine, can I change the hard drives while the machine's running? Probably not. Okay, that's probably the same way for the virtual machines as well. Then we have the SCSI. Okay, so you might have heard of SCSI before. That's what we've seen in VMware as well. You've got SCSI disks, or you even, but sometimes you hear SAS. SAS as well. SAS, probably heard of them, maybe? Yeah, SAS is the serially attached SCSI. So that's another type of SCSI. Just like SATA is the serially attached ATA. So these are generation 2. Sorry, you can have 4 SCSI controllers, 64 devices per SCSI controller. So 64 hard drives times 4, basically, whatever that might be. 256 devices. That makes sense. It's a binary number, so it must be. So generation 2 can boot from them and can modify the devices when the virtual machines are running. Oh, that's interesting, isn't it? You heard the term hot swappable hard drives? Usually on servers, you can have hot swappable hard drives, and on servers, that's where you use the SCSI or the SAS. With the virtual hard disk, you can have fixed size, dynamically expanding, and differencing disks. So we'll talk about that in the next couple of slides. Directly attached disks, or DAS, are local, can be local, iSCSI, or fiber channel SANs. So remember, the same things as what we talked about in the vSphere. So here's some numbers. These numbers are a little bit outdated because obviously every time there's a new version, they're going to make it bigger. So just take this with a more so as a comparison than anything else. So VHDs, that's the file format, so the file extension. So for Hyper-Vs, it's .VHD extension or .VHDX. The .VHDX is the newer type, and the VHDs are the older type. Okay, older type can have about 2 terabytes in size, but the newer type, 64 terabytes in size. Obviously newer, like I said, you're probably never going to use that on a virtual machine as a single disk like that anyway. These are upper limits just for now, but like I said, every new version probably has some improvement. With the VHDX, there's an internal log for enhanced resilience. Okay, and log keeps track of what's happened. So if you keep track of what happened, you can go back. It's like retracing your steps, isn't it? It's like when you heard that story where you had these children just left the breadcrumbs as they're walking, and then when they got lost, they could follow the breadcrumbs back, right? So basically, the logs are like entries. And if you get lost, oh, something's gone wrong. I can see what happened what happened last and reverse it. So that's how the NTFS is as well. It's a transactional database, transactional file system, and similar in this case with the logs. You can user-defined metadata. So I'm sure you've heard of the term metadata for lots of things. When you put metadata, it means you can categorize, you can search, you can filter. So more information you put in there, the more you can do with it. It supports large disk sector support. It's a large disk sector size improves the performance, and this is the default format for anything that's created in Server 2012 R2 or later. So this is what we use now. VHDs is what used to be what we used in the past. You can convert between the formats. So you can, if you have a VHD, you can convert to a VHDX, but obviously the VHDX is recommended, not the old one, but it's still possible. Remember we mentioned how you can have fixed size, dynamically expanding, and differencing this. This is easy to understand. Remember when you create a VMware workstation virtual machine, you can tell it to actually be, I forgot what the term was right now. Let's just open it. So if you remember, when we create a new, let's just add a new virtual hard drive. So when we add, let's pause, can't do that. So when we add a new hard drive, create a new virtual hard disk, you see how this allocates this space now? Or if you don't tick it, you have a size. That's the maximum size. But if you don't tick a lock now, it means it starts off as very small. But as you add data to it, it grows. Obviously, why would you even select this? If you select this, you allocate the whole space now. So if it's a 60 gig virtual hard disk, you get a 60 gig file. But obviously, for us as students and as lecturers and demonstrations, that takes up 60 gigs. That's a lot of space for nothing, right? So why would we ever choose that? The difference is that if you don't choose it, it grows as you need it up to 60 gigs. But if you don't choose it, the performance is not as good as if you do choose it. So you probably heard of the term fragmentation. A little bit? Yeah. So basically, when you allocate disk space now, that whole virtual disk takes up on your physical hard drive right now. So it's contiguous. So if you're adding to it as you're growing along, you're adding to it wherever there's physical space on your physical disk. And because of that fragmentation, the performance is not as great. So it's that idea. But so basically, same idea, fixed space, a fixed size. You allocate storage, large initial size. Let me finish this one point. The creation takes longer. Creation takes time. Without Windows off, load the data transfers. Yeah, Alexi?
Does it create the same problem with the modern hard drives?
Sorry? Modern hard drives?
Yeah, because...
because you're talking about the SSDs compared to the spinning disk. So even the SSDs, I think this is the way it works. It's still got memory addresses. Okay, so it's like solid state memory. Okay, it's got memory addresses instead of sector addresses. Okay, so it's a lot faster, obviously.
Yeah, because there is no moving head. And,
absolutely, it's a lot more efficient. But just from a point of view of, I think it's less of a problem now, but it's more of a problem in the past, and that's why the fragmentation. But even in that, it's a lot easier for just the system to read a whole contiguous space of memory rather than going to the various different locations one at a time. Okay, because they can make it more efficient. Instead of actually addressing each section individually, I can address a whole lump of it. It's a bit like the idea of how IPv6, if you have all these zeros, you don't have to just say all those zeros, you can just have the colons or something like that, okay? Because they're repeats, that's what it represents. So basically, it's a little bit more efficient still, but it's not as big of a problem as you said, Alexi, because of the hard drives reading the tracks, okay? Definitely. But, like I said, this minimizes fragmentation, and you can not overcommit. What does that mean? If you have 10 different virtual machines, each one has 60 gigs, and you have only 500 gigs of physical hard drive, you can't create more than what you have. Okay? That's what it means cannot overcommit. But the problem is, if I have fixed hard drives and these 10 virtual machines, I'm not quite sure exactly how much each one uses. So if these 10 virtual machines, if I was just basic, without thinking about it, 10, I've got 500 gigs, I'll give them 50 gigs each. That seems right, logical. 10, 50 gigs each makes 500 gigs. That's what makes sense to me, it's maths. But the problem is, nothing works out exactly like that, does it? It's just like at home, like you have a family and you make a meal and everyone gets the same share. But the little sister and the big brother, they don't eat the same amount, do they? So just like that, the servers don't necessarily need exactly the same amount of space. Unless we can figure out exactly how much they need beforehand, using this allocate this space now, just means that you're locking away a lot of space that some servers may not need, and other servers actually need more. So that's what it means by overcommit. So this is the best performance. Like I said, it minimizes fragmentation, and it's used in production. Okay. So with the not allocate this space now, it really doesn't. It's in the VMware. It's like what we call. I think we spoke about this. The fin or fig provision. Remember those terms? Fig provision. Fin provision is where we don't allocate the space. Fig provision is where we do allocate this space. So there's equivalence. Whereas the dynamically expanding is obviously the reverse. This is where we don't allocate this space. We just say it's 60 gigs, but really it uses wherever it uses at that point in time. Allocate space as needed. It's a smaller initial size, so it's faster. They can cause fragmentation, like we mentioned, but you can overcommit. Remember that 10 servers, and you got 500 gigs? Well, I can give them all 500 gig hard drives. Probably thinking 10 servers, 500 gig hard drive, isn't that 5 terabytes? Well, not really, because they don't all use 500 straight away. They use wherever they need. If one server needs 10 gigs, the other one uses 20 gigs, and another one uses 100 gigs, and as long as they all add up less than the physical space, it's fine. It's a bit like home. Instead of giving each one a equal plate, your big brother and the little baby sister get the equal size plate, you just put a big pot in the middle, and people just get what they need as long as it's there's enough for everyone. It means the big brother can have maybe 2 serves, and the little sister can have maybe half a serve. And then mum has 1 serve, and the dad has 1.5 serves. You know what I mean? So as long as the big pot is enough for everyone, then everyone's happy. Whereas if you just divide it equally with the fixed disk, you get 1 plate, you get 1 plate, you get 1 plate. The big brother's going to be hungry, but the little sister's going to not be able to finish the food. Aren't they? So this is the same idea. With this overcommit, it means I don't have to worry about this space. I've got 500 gigs. I just give them all 500 gigs. So wherever they use, as long as there's sufficient enough for everyone. Okay, understood? Yeah. All right. So it's comparable to the Windows Server and later. This dynamically expanding can be used in the testing deployment because it firstly saves space. And there's also this differencing hard drives. Okay, so differencing hard drives is a little bit funny to understand. You got a question before we start?
Yeah.
Yeah, what's up?
So we always use fixed hard disks.
Yeah, it's recommended in production. Yeah, therefore that's what it says. But this overcommit thing is something that we're going to address a little bit later for the production as well.
Okay.
All right. So even though this overcommit is preferred.
Yeah.
Yeah. But this is the preferred in production because it gives you the better performance.
Okay. And you will explain overcommit.
Yeah.
How we can do.
Yeah, we can still do both. Yeah. So I think it's coming up later, if I remember this slides properly. So this differencing disk, so the differencing disk is a little bit funny to understand, but let's use something that we already know to explain this. So if we go to our downloads, we've got this virtual machine. No. Let's go to this one. Sorry. This is the server 1, by the way. So we have a VMDK file. Where is it? Here it is, server 1 VMDK. Okay. So the way it works in VMware Workstation is that you create a virtual hard disk file, that's the VMDK, and all the files that you install, the operating system, any data goes into it. Okay. And this one is 10 gigs. Then your lecturer, me, takes a snapshot. And when we take a snapshot, you generate another VMDK file. You see that this is still the server 1, but it's got the serial number at the back now. So the reason for this is that because when we take a snapshot, we really want to not change that, what's the contents of the hard drive anymore, don't we? We want to preserve it, because when we go back to the snapshot, it must be exactly that content. So therefore, when we take a snapshot, we stop using that one. Stop using that one as the disk to write to. We still use it to read from, because it still contains data. So if we make any changes, we write to the next VMDK file. We take another snapshot, that gets frozen, and we create another one, and so forth, and so forth, every time we take a snapshot. You get me? But you can see that these are all different sizes, okay? And this one's 10 gig. That's because that one is the initial one. That's why we put the whole operating system on there. That's why it's 10 gig, okay? But then we made a little bit of change. We probably installed Active Directory domain services. Then we took a snapshot. Then we created some users. We took a snapshot. We did something else. We created a snapshot, and so forth. But so therefore, all of this, the size of this is basically the difference. Changes that's occurred from the previous snapshot. You get me, guys? So the changes or the difference. So basically, if we're talking about differencing disks, we have a parent, and then these are like differences from the original parent. Okay, stores changes from the parent disk. Parent disk should not change. Differencing disk isolates the changes, and you can have multiple differencing disks can come from the same performance, and this increases the overheads. So because in order to get all the files, I must read this. If this is the sequence, okay, I must read this, and I must read that to get everything. So every time you have to increase the complexity, it's going to decrease the performance. So it can be used for standardized based images. So basically, remember the clones, the link clones. The idea of the link clones is like this. You have the parent disks, you make the clone, but the clones only contain the differences. So with this, we can actually create standard base images, but you should avoid this in production. Okay, so it's good for practice, good for development, just like snapshots, like I mentioned before. Snapshots are great for what we have to do, but you should avoid snapshots in production. Okay, because when you go, we all know, one easy error to remember is when we restore one of our computers in Active Directory, if you restore it to a snapshot, then you lose that trust relationship, right? That's one of the obvious problems. What about even, we talked about this in the past as well, what about domain controllers? Can you even restore them to snapshots? Because what about the RID? If you don't know what the RID is, remember every computer in a Windows Active Directory or every object has what's called a SID, security identifier. It's like a unique number, like your student ID. Everyone in there should have something different. But if you go back to a snapshot, if this is the original, you create 500 users, so you use 500 RIDs to make this 500 SIDs. Then you're here now. We took a snapshot here before we created 500 users, and we are here now. But for some reason, we have to go back to the snapshot. What happens to the 500 RIDs that we just used? Are they still available now? And if they're still available, what happened when we get SID conflicts? So basically, this for the same reason and other reasons, these should be avoided in your production environment. So basically, if we have these files, file A, B, and T, they become read-only in the parent, and it grows. And when you're reading, you read some from the parent, and you read some from the child disk. And when you modify, you only modify what's on the child disk. You don't modify the parent. There we go. Create, modify, whatever. Same thing only on the child. Even deletions only on the child. Just like with our snapshots. So directly attached storage. So virtual machines directly attached to physical disks. We all know that. We can actually, that's a little bit different. What this means is we can have a physical hard drive on our host, and we can actually tell a virtual machine to directly just use that one. It's not a good idea. It's not a really good idea at all. The reason why it's not a good idea is that that means that virtual machine is directly attached to a physical hard drive on that host. What does that mean? It means that virtual machine is tied to that host. It cannot move. Okay, all those advantages of restarting, a live migration, etc., does not apply to that computer virtual machine anymore. But it's possible. Okay, but the disk must be offline before it can be used. So it must be offline for the host before it can be used by the virtual machine. So the lungs on a iSCSI or fiber channel, so we sort of already know about this. They're storage area networks, and the lungs are logical units, can be directly attached to a virtual machine as well. But that's fine because that's not on the host, that's somewhere else. So if the virtual machines move, they still can reach those lungs elsewhere, that's fine. Pass-through disk considerations. So pass-through disk is the best performance. It's a limited size. It requires the lowest CPU utilization, but there's no checkpoints or differencing of the virtual hard disk, no portability or encapsulation, and it's not part of the Hyper-V backup. So this pass-through basically is using the hard drive, and it passes through the system and uses the hard drive directly. So the CPU is not used to make any computations to actually use a virtual hard disk. You can't have any of these. What about hard disk sharing and quality of service? So this provides shared storage for virtual machines. So we can use a shared SAS disk by virtual machines. That's many virtual machines connecting to the same SAS disk. The hard disk must be using VDX format. It must be connected to a virtual SCSI controller, and it must be stored on a CSV or cluster shared volume, and it must be using a scale-out file server using SMD3. So these are some type requirements. So this is a separation between the infrastructure and the virtual machines. There's also what's called storage quality of service. You've probably heard of the same term, quality of service. But basically, that's prioritization. Prioritization on your switches, right? Okay, prioritizing some traffic over others. So if we're talking about storage quality of service, it basically restricts disk throughput. It's configured per virtual hard disk, and then obviously some are prioritized over others. It's dynamically configurable while the virtual machine is running. So some considerations. So virtual hard disk consumes a large amount of space. We all know that. And can increase over time, and so we need to monitor it. So if we have somewhere that we're storing a virtual hard disk, and the virtual hard disks are growing, it eventually can fill up that location. If it fills up that location, your virtual hard disk cannot grow, or you cannot add any more bits or bytes, then eventually your virtual machines could possibly crash, can't operate. Where you store the virtual hard disk is important as well. So if you store it for some reason on the same hard drive or same partition as your operating system for the host, for example, then potentially you could grow so much that you have no space for the operating system to actually create temporary files, and then it'll crash the whole host as well. We can use multiple physical disks for better throughput. Okay, so multiple physical disks is like your RAID setup, your RAID with hot spare, and obviously they can improve the performance because we can read multiple copies and write to one copy, which then replicates. We can use redundant storage spaces. Okay, redundancy, that protects against failure, obviously, and we all know that SSDs dramatically increases performance. SMB file shares, SMB-free file shares, so like I mentioned last week, you can create a shared storage from a Windows server. So you turn that Windows server into a SAN controller, basically, and you can create what's called a share for applications. Okay, that's not your normal right-click share. That goes through your server manager, you create a new share for applications, and that becomes an SMB-free share, and that's where we can actually put our virtual machine files. We can use storage SANs for storing virtual hard disks. They are usually specialized, they're redundant, they're fast, and the shared storage basically allows for all those functions that we like the failover, high availability. So it's called failover clustering here, but in the VMware it's called the high availability. It can be used, and obviously makes the line migration or vMotion a lot easier. We should exclude virtual hard disks from antivirus scanning because they're big files. And to be honest, this is from the host point of view. The host is not going to find anything on the VHD or VHDX. It's not saying inside the virtual machine. Inside the virtual machine, you still should have your antivirus like normal, but then you're scanning from inside the hard drive, not from the host point of view, which is outside the hard drive. From inside the hard drive, you can actually find the actual files. So creating virtual machines, so I think this is fairly easy to understand most of the time. Virtual machines has virtual hardware. Only devices that Hyper-V support can be used. Okay, the virtual hardware can be emulated, which is available during boot. They can be synthetic, which is available for only supported operating system, or they could be this SRIOV, which is a specialized bit of hardware, which is only supported certain operating systems. But they're basically hardware that takes them, so you've got physical hardware, okay? If you, on your server grade machine, you've got this physical network card, which is designed for virtualization, or for a server that's going to be virtualizing virtual machines, then it has this SRIOV capable. Okay, so it's just a term. And then when we virtualize and we add a network card into the virtual machine, and the host and the guest operating system is also capable of this, we can just basically offload or pass through some of those functionality directly to the hardware, which makes it perform better. Prior to 2012, our only generation virtual machines were available, but now we have generation 2, which basically makes it better, as you would expect. Emulated devices are removed. We can use the UEFI firmware instead of BIOS, which gives us secure boot. We can also boot from the Pixie controllers, SCSI controllers, and we can also use the Pixie boot. So everyone understand what Pixie boot means? What is it?
You just load, you just press the button and load from the network.
Yes, pre-execution environment boots from the network. Boots downloads the image from the network and runs it in memory. So it also supports faster boot and operating system installation, can run side by side with your generation 1 virtual machines or your old legacy servers. And obviously with the generation 2, it supports Server 2012 or later and 64-bit versions of the Windows client. So again, this is things we already know in others. We can configure the virtual machine settings. Only limited options are available during creation. So when you create it, you've got some settings you can configure, but there's a lot more after you create it. You go back into the settings and you can see a lot more options. Configuration options depend on the generation of the virtual machine. So if you've got generation 1 or generation 2, you might have different things to configure. Most settings can be configured only if turned off. So like I said, if we want to configure the hot swappable RAM support on the virtual machine. So what does that mean? That means we can add or remove virtual memory from the virtual machine. We need to make sure that virtual machine is turned off. Okay, like the virtual hard disk, they need to be turned off. So some settings, just like I said, you treat the virtual machines a bit like how you would treat the physical machines. The things you can do while it's on, the things you can do while it's off, it's probably the same. So for example, adding or removing hardware components, you probably have to be off. Configuring the memory or processor and disk settings, you have to be off. A few settings are configurable while the virtual machines are running. These include configuring the network adapter, so like unplug, plug. If you compare that to a physical machine, can you unplug a physical machine from one switch and put in another switch while it's running? Yes, so you can do it on a virtual machine as well. That's what it's basically saying there. Adding hard disk, adding a hard disk to a SCSI controller, that's equivalent to your hot swappable hard drives in a real machine. Disabling or enabling integration services. So if you don't know what that is, that's equivalent to VMware tools. So if you install VMware tools, we all know what it does. If you have integration services turned on in your Hyper-V virtual machine, pretty much does most of the same things. And we can use the PowerShell commands to do some of these things as well. What is dynamic memory? So dynamic means changing. Obviously, we're talking about RAM. So we spoke about how in VMware, RAM, there's contention. When there's contention, there's a fight over the RAM, physical RAM. And obviously there's the virtual RAM, virtual memory, which is the hard drive, which is not good. So basically, what is dynamic memory? It's a way of using memory more efficiently. Okay, it's a more efficient use of the available physical memory. Shared resources that can be reallocated automatically. Demand, based on demand, available memory, and the settings of the virtual machine. So dynamic memory settings include, how much RAM do we give it during startup? So we all know that startup is a time when the virtual machine, the operating system are being loaded. That's where they need to do a lot more work. So maybe we can actually give more startup RAM just to get it to boot up faster. There's also minimum RAM. So remember, this is not how much RAM you allocate to the virtual machines. This is how much physical RAM the virtual machines are getting. Minimum RAM can be decreased while the virtual machine is running. Maximum RAM can be increased while the virtual machine is running. And there's a memory buffer, which is a percentage of extra memory to reserve for the virtual machine. And memory weight, which is a prioritizing memory allocation when the physical memory is low. Remember when we talked about the resource management in the vSphere? Basically the same thing, just different ways of saying it. So we called it shares. Yeah, we called it shares, but now it's called memory weight. The maximum is basically the reservation. The minimum is the guarantee. This is the maximum is the limit. The minimum is the reservation. And the startup RAM is something that we didn't have in the VMware really. So basically, if we have a look at this diagram, these are the configuration. We've got the startup RAM, which is 1 gig. The minimum RAM is 512, and the maximum RAM is 4 gig. These are, we're talking about physical memory now, okay? So these are free virtual machines. This is time equals 0, 15 minutes, 30 minutes. And the whole system has 8 gigs, okay? The host has 8 gigs of RAM. So what happens? So right now, all of them are using 1 gig. Maybe they're all starting up. Okay, they're all starting up 1 gig of RAM. All right, so basically, if that's 3 gigs, because it's free virtual machine, total is 8, that's about 37.5%. No one cares, that's plenty of memory. 10, 15 minutes later, you can see that the virtual machines are running for 15 minutes, and now the finance virtual machines are using 3 gigs. That's still 1 gig, that's 2 gig, now that's 6 gigs, okay? So now it's, again, 75% of the of the physical memory is being used. But now, a new virtual machine is being started up, and that's using 1 gig. This one's dropped down to 512. This one's increased to 4 gigs, and this has gone down to 2 gigs. So what it's trying to illustrate is that the amount of physical RAM each virtual machine uses could change based on what's available, who's fighting for it, and so forth. What about smart paging? Remember when I talked about the virtual memory? Remember smart virtual memory? Like we said that in the Windows it's called paging, okay? In Microsoft it's called paging. So what is smart paging? Memory management technique that uses the physical disk resources as temporary memory, so same thing, virtual memory. So like I said, there's always equivalence between what we talked about before and what we're talking about now. It ensures that virtual machines can always restart. So what does that mean? If the virtual machine is running and you restart, when you're restarting, when you're turning off, you give away the memory. You're not using the physical memory anymore. But when you restart, you need the memory back. So this smart paging ensures that the virtual machine can always restart. During the virtual machine restarts only, if the Hyper-V is low on memory and the virtual machine has more startup minimum RAM, then the memory cannot be reclaimed from other virtual machines, the smart paging is used to allow it to start up. But like we said previously, when we talk about virtual memory, it's slow. So it temporarily degrades the virtual machine performance. It's used only for a limited time and then removed. It's not used when the virtual machine is started from off state. The virtual machine operating system paging is preferred. And if we look at this, the sales virtual machine and service virtual machine can be restarted only if paging is used. So if we look at this, these are running, so that's 3, 5, 6, 7, but then they're running, but as soon as they restart these two, it'll increase to 4 each. That's 8. There's no more RAM, isn't there? So therefore, if there wasn't any smart paging, these machines when they go to fire back up, I need RAM. I need 1 gig of startup RAM, or there's no RAM there. So in this case, if there wasn't the smart paging, it could do nothing until those virtual machines drop down or something like that. But with the smart paging, they are allowed to restart even though there's not enough, even though it's not the physical RAM. So the integration services, like I said, makes the guest operating system aware that it is running on a virtual machine. Many operating systems include integration services. It installs the latest integration services, the VM bus and synthetic device support, and there's time synchronization, mouse release, volume shadow services, and it's managed through the virtual machine settings. So remember what I said about the VMware tools? So basically, when you install this integration services, you install these services into the guest operating system. In the integration services, we can turn off any of these things or turn on by ticking or unticking. Yeah, Alexi?
Just to clarify, so this paging is switched on every virtual machine.
So this smart paging is on the host.
On the host.
Yeah, so it's not part of the virtual machine. So if it looks like this, if you look at, where is it? Virtual machine operating system paging is preferred. What's this talking about? It's not used from basic start off. So this is talking about the paging that's inside the virtual machine here, but the smart paging is on the paging that's on the host.
So it supplies the paging for all the version. Yeah.
Yeah, you get it? Yeah?
Yeah.
All right, good. So with this integration services, just the easiest way for you guys to think of it is VMware tools. Remember what we said that VMware tools gets you that heartbeat. Say, I am alive, to tell the host it's running. It does the time synchronization with the host. It does the data exchange, which is basically the copy and paste. It does the backup service, which is the volume shadow services, and the guest services. And these are the services that's installed inside the virtual machine because of the integration services. So this is the virtual hardware, okay? So this is in the, what you see in the on a physical machine sorry, I'm reading this wrong. we're talking about integration services, so my brain was lost. So this is what you see on a device manager without integration services. So some of these hardware, like this Microsoft SCSI initiator, the standard VGA graphics, the Intel whatever PC adapter emulated. So that's without integration services. With integration services, oh, look at that. Now instead of being a generic VGA, what's a graphic adapter, it becomes a Microsoft Hyper-V video. This becomes a Hyper-V network adapter, and this becomes a Hyper-V SCSI controller. What does that actually mean? This means that it's trying to find some generic drivers for these virtual hardware. You know how it is with generic drivers. It sort of works, but it's not the most efficient. You get me? It's like you taking a car off-road. If you have a normal car, it's got normal tires, it sort of works on the off-road, but it's not ideal for it. It's probably not as efficient as it could be. So once you install integration services, now you have the specific drivers for that hardware, which actually allows the interoperability to be a lot more efficient. Okay, using virtual fiber channel adapters, so access to fiber channel SAN storage from a virtual machine. So what are we talking about? We're talking about SAN in the real world, and we're talking about a virtual machine. Okay, not the host, the virtual machine. So it's a Windows Server guest operating system, and we can create what's called a virtual HBA, host bus adapter, and we can actually link that virtual machine to a physical SAN directly. So this is not the same as storing your virtual hard disk on a SAN. This is actually linking the lung from the SAN directly to the virtual machine with a virtual fiber channel adapter. We can use the virtual SAN manager to configure a virtual SAN. The virtual SAN channel fiber channel adapter maps a physical HBA, and the virtual adapter can connect to the virtual SAN. The storage hardware must support the endport ID virtualization, so that means that that actual hardware has to have that support. Like I said, a lot of hardware now are designed for virtualization in mind. That means you can offload a lot of the processing, and they allow you to use it for these extra functionality. So the virtual machine can have up to 4 fiber channels. Okay, so supported virtual machine for live migration, virtual machine fail level cluster. So if you want to compare to what we know, vMotion, high availability. It just Microsoft names for the same type of things. There's also this MPIO, multipath input-output, multipath to the SAN, so which allows for multiple redundant paths. What's not supported is you can't boot from the fiber SAN if it's mounted in this way. The checkpoints do not include it, obviously, because these are hardware locations. And host-based backup is a host backup. Live migration of the SAN data is not supported. All right, so this is really basic. How can we install a virtual machine, the operating system? Well, we can still install from bootable CD-ROM. So we can mount the physical CD-ROM into the virtual machine, just like we've done. We can use ISO, and we can use network deployment, like we talked about with the Dixie boot. We can use the deployment server to deploy a virtual machine over the network. We can even just copy a virtual hard disk with an operating system, put it somewhere, and create a new virtual machine to use it. Okay? I think I've done that many times with VMware as well, because sometimes students come up, oh, my virtual machine is not working properly. Something's gone totally wrong. So what I've done is just copy the VHDK files, I put it in a new location, and when I create the new virtual machine, instead of creating a new disk, you use an existing virtual disk. Because the virtual hardware is exactly the same, it just boots up and You can use it all anyway. So I've rescued a couple of students' work by just using that method. Because the original virtual machine, I don't know what they did to it, but the data is still on the hard drive. We just tried to create a new virtual machine based on that hard drive. So this is talking about the same thing. So this is similar to cloning, but if we do cloning, that's like we've done that with our golden master and so forth. You need a generalized operating system. So that's when we use the sysprep. We can use differencing disks where the virtual hard disk should be first generalized and the parent hard disk must not then change. So that's like the link clones. Importing virtual machines. You can import virtual machines without first exporting it. Only virtual machine data are needed. Over 40 different types of issues can be detected as part of this. Because if you're exporting a virtual machine, what if that had a parent? What if the virtual disk, a virtual switch is not available on the new server? The virtual machines can have all these problems, but these problems can be, some of them can be fixed. So the import process, you should create a copy of the virtual machine's configuration file, validate the hardware configuration settings, compile a list of incompatibilities, display the incompatibilities, ask for new settings, remove the configuration file copy, and you cannot restart older save states or checkpoints. So to be honest, if you're going to export, just delete all the checkpoints first. Checkpoints and snapshots cause so much problems if you're trying to do some sort of migration. So when you remember we talked about what if you had VMware virtual machines and you wanted to make it into Hyper-V? First of all, delete all the snapshots. The number one task in a lot of procedures is delete all the snapshots. Then you use the converter to convert. Virtualizing a physical computer, I think we spoke about that even in the Cert for VMware workstation subject. There's a thing called P2V, physical to virtual conversion, and we can actually convert a physical server to a virtual server. We can also use a disk to VHD, which converts a physical disk to a virtual hard disk. So what is this useful? Well, what if you have physical deployment of all your servers? Do you want to reinstall, reconfigure everything? Maybe that's the best way actually. Or maybe you can just use the P2V for now before you create various copies of it. So here's a picture of the disk to virtual hard disk converter. So this is how you can convert a physical disk to a virtual hard disk. Okay, what about virtual machine connection applications? So just like vSphere, there's no just console window straight away. It just runs. Okay, it's running in the background. No one needs to look at it because it's a server. It's not a VMware workstation where people are actually actively doing on it. But when we double click on the virtual machine, we can actually launch a console. So this is what it looks like, and then you have some menu items at the top. So this is installed as part of the Hyper-V role, or you can install it as part of the RSAT, which is the remote server administration tool that you can install just on your desktop machine, and you get the administrative tools, or you can just use a remote desktop. Hyper-V administrators can connect to virtual machines. You can restrict access by using this revoke VM connect access commandlet. Remote desktop connections to a virtual machine. The virtual machines can be without a network connectivity. Devices can be redirected. So that's where you map your physical printers, drives, hard drives, various things to the virtual machine. It's a bit like the idea of when you have if you have a virtual machine running, then you can go to the VM tabs, you've got the removable devices. Well, that's not really good. Let's try this one. So this is like the VM tab, the removable devices, and you can actually connect your physically plugged in devices to your printer, printer, smart card, physical network adapter, your USB drives, etc., etc. So that's basically the same thing. The remote desktop services component is used. So basically when we do this, it's almost using the remote desktop services to connect to the virtual machines. We need to be enabled at the Hyper-V virtual machine connection at virtual machine level, and the guest operating system must be one of these. Checkpoints, like I mentioned, checkpoints are like snapshots. So if you look at it, it's just called checkpoints, but effectively it's exactly how we understand snapshots. Okay, so we can see this is like the snapshot manager, and obviously just like snapshots is a point in time backup. But primarily, it's used for testing and development environments. Like I mentioned several times, snapshots should not be used in production. It can cause problems. It can cause issues with distributed production environments. You can create differencing disks, which decreases performance, and you cannot create directly attached disks because directly attached disks are physical disks that are attached. It's not part of the snapshot or checkpoint. So what happens when you take a snapshot? Was checkpoint when created, a checkpoint cannot be modified, can only be viewed, applied, exported, renamed, and deleted. Checkpoints creation, it will pause the virtual machine, it will create a differencing disk for each of the disks, and create a copy of the virtual machine configuration, and then it will resume the virtual machine. So it happens while it's doing it. It's almost like we don't really see it. It's all doing that. It also creates a copy of the virtual machine memory if it's running, obviously. So if it's running, when the checkpoint is created, it has a configuration file, it has a save state file, that's where the virtual memory is saved, and it has a differencing disk. And with these checkpoints, we could delete it. So this is what basically happens, what I showed you with VMware. But you have a VHD. We take a snapshot or checkpoint. Any more changes is changed to a new file, but the original file is static, not changed. We take another snapshot, a new file is created again, and any changes is applied there, and these two are locked in place. But, oops, sorry. But then something happens. Something happens in the sense that, hey, I want to go back to I want to delete this snapshot. If we delete this snapshot, we merge the, sorry, I'm reading it wrong. So if we go back to a snapshot, then all these changes are deleted, and we start again. But then what if we want to delete a snapshot? So if this snapshot we don't need anymore, it's an old snapshot, we don't need it anymore. When we delete it, that becomes part of the parent. And then any more snapshots are generated. So exporting your virtual machines as checkpoints. So exporting virtual machines is not required. You can just copy the virtual files like we've been doing. Exporting virtual machines also consolidates files. So basically, what does it mean? It deletes all the checkpoints and makes one big file. Alexi.
What's the point to delete checkpoints?
Save space. To save space, really. Like for example, even though you
when we merge the files, it will be smaller.
Yeah, it'll be more smaller, slightly smaller. So you probably notice that yourself. The more checkpoints you have, it's because don't forget. So this is one situation. If we had this big file here, which is a parent,
yeah,
we take a snapshot. Let's keep it simple. We delete 10 files. It's 10 gigs. Okay, so we deleted it, but it's still in the parent. Then we add another different 10 gigs. It's still building up, isn't it? So we by actually deleting this snapshot right here, those 10 gigs that was deleted is actually gone. You get me?
Yeah.
You're not keeping anything that is deleted, first of all, But also, even if you don't delete anything, every time you take a snapshot, it's a sliding, there's overhead on it. Yeah. So, and also, like I said, snapshots are not good for production. So I'm sure in your own practice, when you're doing the assignments, when you take a snapshot, you take lots of snapshots, you notice your virtual machine getting bigger and bigger, right? And when you clean up the snapshots, you notice it reduces in the size, right? As well, hopefully you notice. So that's what a lot of people do. Okay, sorry, let's get back to here for a second. So when you export, you consolidate files, you're basically deleting all the checkpoints or snapshots, and you're consolidating all the things. Exporting a checkpoint only as a single state, the difference in disk and the checkpoint hierarchy are merged. Live export, you can export while the virtual machine is running. We can update the integration or the VMware tools type thing after import. Issues with checkpoint. So we sort of talked about this a little bit. So when you apply a checkpoint, you're going back in time. Okay. So one of the things that could affect is including the vector clock synchronization. So the vector clock. So basically, if we are all in the same trusted area, what you know and what I know should be exactly the same. Okay. What you know of the current time should be exactly the same. So in a distributed application, so what's distributed? That's where it's not only one server hosting the application. Think Active Directory, for example. You can have multiple domain controllers, but they all have a copy of the Active Directory. That's why it's distributed. What if one of them goes back in time? Then they have a different picture of Active Directory to everyone else. Who's right? Because Active Directory replication is replicating between the servers, and other things include the DFS replication, SQL server replication. Applying checkpoints rolls back the logical clock. Members of the replica set are not converged at the same state. So who is right? You get me? Just like when you have argument with two people, if both of them think they're right, it's a very no one wants to give in. There's problems, isn't it? So with cryptography as well, so cryptography is obviously creating encryption based on keys and also environmental elements such as what is the current time, how long is your key valid for, etc., etc. Reducing entropy. So you know how
Gauss distribution.
That's right. Remember, what's it? Randomness. Okay, because everything's programmatic, how can it be random? You know what I mean? This program tells it to do this, to do this, to do this, to do this, and how do you make it random? Because it's a set structure of what they have to do, right? So the way the way they do it is they use some silly technique. I'm not a programmer, so I won't tell you exactly how it goes, but basically they do this and do that to introduce a pseudo-randomness. Pseudo means it's not truly, but it's like it's random. So basically, if you go back in time and you repeat history exactly how it is, you're probably going to end up with the same result. So basically, what this is saying, entropy means chaos, disorder, okay? So entropy, that's what it means in scientific term, it means chaos. So basically, if we're going back in time and we still follow the same procedures, we're going to probably end up with the same result, which means the chaos is not going to be chaos. It's predictable. So basically, with cryptography, the chaos of the random data may not be as random as you think. That's what it's saying. How much do you care about that? Not much. Okay, it doesn't really affect our lives. It just means there could be a problem. Distributed applications using the vector clock algorithm has no awareness of running virtual machine environments. So think of when you revert one of your Windows domain members to a previous snapshot, you lose that trust relationship. That's why. Okay, this is the reason. It removes changes in the virtual machine as if they never happened. For example, if the user data is lost, password are reverted. So you reset the virtual machine to like 5 months ago, your password might have been different. So your current password won't work and you have to remember your old one, regardless of whether they were already synchronized or replicated. So here's that Active Directory situation. You've got two DCs that replicate. This DC creates 100 users. Sorry. This DC has a RID pool between 500 and 1,000. So just that's the range, okay? So we take a snapshot. We create 100 users. So now the RID pool has reduced by 100, right? Okay, so replication happens. This 100 users is replicated, and now right before it had 100, now it has 200 altogether. So far so good? Yeah. Yeah. Then we apply a checkpoint. So we go back to a checkpoint. You see this RID pool? It's gone back to 500 to 1,000 again. It's almost like that first 100 is not being used. So if the RID is not used, that means if we create another object on that server now, it will use that first RID 500 to create a new object, and that SID will be identical. So now it creates another 150 users, but that first 100 is using that.
Overlaps.
Yeah, overlaps that other one, doesn't it? So it's only the last 50 which are different. And then when we have a synchronization, only 50 users are replicated to both domain controllers. Others are either in the first or second domain controller, and 100 users have duplicate SIDs. Big problem. But trust me, this never happens. This could happen because that's the theory behind it. This will not happen because they would lose their trust relationship first. Okay? So this is a problem. So we never really do this with domain controllers, but we do. But what we can do is that now with the newer operating system, they have what's called a generation ID variable. Okay, every time a snapshot is taken, that variable increases by 1. Okay, but so basically the generation ID is designed to address the issue of reverting to a past state. It's a 64-bit integer tied to the virtual machine configuration. The generation ID is passed to the virtual machine in the BIOS, and applications can compare the current and previous values. If the values are different, then something has happened. Go back to the snapshot. The hypervisor, meaning the Hyper-V, must support the machine generation ID. The guest operating system must also be aware of it. So if the generation ID are different, so for example, that the domain controller, go back to snapshot, the generation ID will be different, okay? Then it will just basically be, this is rubbish. Whatever this machine knows is rubbish because it's gone back, it's a different generation ID. So just delete all the SID, delete just everything that's in there. So here's in the virtual machine, here's the generation ID counter, and here's the generation ID actual number. It's a hexadecimal, as you can see. And here's the current generation ID. You can view it like that. But when it detects that the generation ID is different, just 1 second, it just says everything I know is wrong. All my SID is rubbish. So as a domain controller, I would delete my SID, chuck it in the bin. I will go, so my RID pool, I'll chuck it in the bin. I'll go to the RID master, which is a special domain controller which controls which domain controller has what pool. Okay, gives them the numbers, and I'll get a new pool. And also, my Active Directory is rubbish, so I'll just pretend I'm a new domain controller and ask every other domain controller to replicate to me. So that's how they address that issue. You had a question?
Yes. Why does it need that huge generation ID?
Oh, why? Because then it can tell the difference between one generation and another generation.
Yeah, but it might be like 1, 2, 3, and so forth.
Yeah,
you
obviously.
Don't need like
16
digits.
No, you probably don't, but obviously it's a 64-bit, and that's how they've designed it. And obviously it just means that you can have more numbers. If you have a 1-bit number, for example,
yeah, but they haven't started, so I don't believe they made that many changes.
Yeah, this is
so they started from something.
Yeah, they started
9 something.
Yeah, so they started from a number, and obviously it progresses from there. But obviously, like I said, we're not the programmers or electronic engineers that designed this. The fact of what we need to know is
Maybe they code like in different parts, different, I don't know, areas.
Possibly, maybe, but that's not something that I definitely know about. As why is it so long, and why don't they just have 10 digits instead of 16 digits?
Yeah,
whatever?
maybe not 10, but
Yeah, well, 5 or whatever,
Yeah.
But that's what they've decided, okay?
Okay.
Yeah, so that's what we use. The key thing is that they detect different numbers and they say that something's changed, and from that they perform those actions. Okay, performance monitoring. So we've spoken about performance monitoring in your previous subjects. This is basically we can monitor operating system and applications using the system resource, provides up-to-date information on performance, gives you a bit of a health of the IT infrastructure, and allows you to compare your current activity with previous activity, or baseline, or benchmark. It allows you to plan for future requirements. So remember, the performance monitoring, if I create a baseline, so I've just installed the system infrastructure and I monitor it. I'm measuring the CPU, I'm monitoring network, I'm monitoring memory, monitoring all these special critical resources. And I monitor at 9 a.m., 12 midday, and 3 p.m. And I do it for 15 minutes every day for 2 weeks. I store it. 6 months down the line, I perform exactly the same monitoring, exactly the same length of time, for the exact same counters. Then I can take this baseline and what I've done now and see if there's a trend. If there's a trend, that means I could say, oh, it's going this way, my limit is here, this is the amount of RAM I've got. In 6 months' time, if the trend keeps on going, my limit is going to be a limiting factor. So maybe before, in 6 months' time, I do some sort of upgrade. I increase the amount of RAM, I change hosts, or I do whatever I need to do to prevent this problem. So it allows you to detect problems, be proactive, so proactive and make changes before they become a problem, or it can be reactive by looking at historical data and working out problems as well. So the performance monitoring works out if you need future requirements for increasing resources or performance. Windows servers include several tools: operation managers, centralized monitoring, alerting, and reporting for the enterprise. So here's the task manager. We've seen this before. That's just live information. Talks about the amount of CPU, memory. This is the resource monitor. Again, live information, more detailed about the critical resources like CPU, memory, disk, and network. Your typical ones you monitor. But you can also use the event viewer to look at your logs for historical problems. And you've got this reliability monitor, which actually gives you a graphical tool to show you how reliable your system is. And basically, wherever there's an error, the reliability drops. But this is probably the most important one. Performance monitor allows you to create those benchmarks or baselines. Okay, I think in Cert4 you all did that already. So we can put whatever counters we want, and we can measure it. And this is live information, but we can save it and then compare it to it later. So with the Hyper-V hosts, only performance monitor can monitor the Hyper-V. Many Hyper-V performance objects are added. So where you install the Hyper-V role, there's additional performance monitor objects. So all of these things here, you got extra ones for the Hyper-V. So for example, logical, these are some of the important things to monitor. Logical disk, average, disk 6 reads and writes, memory available megabytes, and so forth. Okay, I'm not going to go through all of them. With the virtual machines, the virtual machine tool monitor the virtual environment. The heavy utilization in a virtual machine does not always mean heavy utilization on the host, because it's obviously got its own set of hardware restrictions, or vice versa. Available resources resources are adjusted based on the server load. Memory disk counters are the same as on the server, so these are the things we could monitor inside the virtual machine. So that's what you have to do on the host and inside the virtual machine too, because you need to know how your virtual machines are running, but you also need to know how your server's running. You can't just do one. There's also resource metering. So this is where we can track resources used by the virtual machine or the pool. They obviously are the disk, memory, network, processor, and we can use that for chargeback. So this is where we can have this department or this customer is using this much resource, then I can actually charge them for it. So in a public cloud, for example, that's something they would use. Okay, so configured, we can configure by using the PowerShell. So we're not going to talk about the PowerShell as well, the commandlets, but we can use graphical reporting is not included, obviously. So that's the end of today's presentation.